My name is Trevor Grant. I'm a PMC on Apache Mahout and Apache Streams, an open source evangelist, and I've recently dubbed myself an AI engineer at IBM because, as you're about to see, I'm all about buzzwords and staying very relevant. How many people have seen Battlestar Galactica, an old sci-fi show? A couple of hands? All right. This talk evolved somewhat since I started. It is now about building your own Cylons from Battlestar Galactica. We're still going to cover a lot of the facial recognition with Apache Flink, but it's a fun way to kind of ham this up. The majority of how we do this is we're going to use all off-the-shelf libraries and components. It's a really exciting time we live in that, like, stuff to make what was science fiction maybe 10 years ago is available off the shelf and open source now, Apache Software Foundation and other places. And that's kind of what I want to drive home today, is that it's out there for anyone. But I'm going to start with just getting straight into the how facial recognition works. So we have a Cylon, or a drone, if you will. These drones you can pick up on Amazon for about 80 bucks a pop with a little webcam. You can get as many as you want. I don't know if you saw, but the gist is we've got streaming video coming in off of a webcam. We want to pick out the face and then decompose the face into, my animations aren't working right. It's a rough day. We decompose the face into a thing of pixels. We can do an ordinary least squares regression and decompose a linear combination of the Eigenfaces. Goes to Solr. Solr, we search Solr for the appropriate face, whose the face is. It comes back, we recognize the person. That might have seemed like a lot to throw at you really, really fast, but I kind of wanted to do the overarching, like, what it is we're doing here. So first off, let's talk about the cascade filters. We're not using neural nets. Everyone loves neural nets and deep learning, and everyone thinks that's so cool. But the problem is with the neural nets is that's not effective. When you're trying to do real-time video recognition, even for just scoring and picking out faces, it takes a lot of hardware. And when you start talking about cheap little edge devices, they just don't have it. So we use something, OpenCV is Open Computer Vision. It's a really cool library I recommend checking out. And they use something called a cascade filter. And the way a cascade filter works is it looks at rectangles and looks for patterns of, like, dark and light rectangles, and in that way can pick out where a face is. For example, on any person's face, this area is dark, the eyes are always dark, and there's a light spot in the middle. So we turn we grayscale out the image, which my levels are a little off, but you'll have to believe me that that's gray. It looks more gray. And this is kind of an animated whatever, but it finds these patterns of light and dark that it's been trained on, and it's able to do this while it might sound a lot like a neural network, if you've done some deep learning, it's significantly faster. And I once again want to say that there is artificial intelligence, and there's exciting things that were going on, and everything isn't a neural network. The next thing we want to do, so that is how we detect the face, but we don't know who this is. All we've done is we're picking out in video frames, we're picking out the faces, detecting this facial detection. Now the next part that's important is we want to be able to do facial recognition. Given a face, how do we recognize that this face is Sally and this face is Joe, or the case may be? And for that, we use another much older but still very efficient and a very efficient method called Eigenfaces. And the way Eigenfaces work, we once again have just a regular color image, or the frame, if you will. We grayscale it. And if you think of a image is really, a grayscale image is just a bunch of pixels. And all these pixels are black and white, so we can represent each pixel as a number. There we go. And while that's a matrix, we could flatten that matrix out into a vector. And so we can represent any face as a vector, is the idea there that I'm trying to get at. And then we can take a number of faces, flatten them out into vectors, and we've got now a matrix of faces where the images are the rows and the columns are like a pixel position you can think of. That makes sense. Now, if you go back and remember back to some like high school, maybe early college linear algebra, we can do a matrix decomposition. And we want to break that matrix of faces up into what are effectively the eigenvectors. But we're going to call them the eigenfaces, because just like that's the good one. Just like we could take images and stretch that, we could take an image and stretch it out into a pixel, or stretch it out into a vector. We can take those vectors, those eigenvectors, and like turn them back into images, and this is basically what they look like. And so the point here is we can then take any face, and instead of having a picture of 250 by 250 pixels, we can have, in this case, maybe 130, a linear combination of 130 eigenvectors. And that's how we can represent all, like, we can have an entire index of faces, an entire collection of faces, where each face, instead of being represented by 62,500, some long image of pixels, we just have these eigenvectors, like the principal components of the face that make up that face. And then when we take new faces in, and this is the really exciting part, neural networks have a really hard time with new faces that they've never seen before. We can take any new face, and we basically can just do like a simple linear regression. And the betas are, once again, so we regress, we take this face, turn it into, the new face turns into like our Y vector. Our old eigenfaces that we've computed previously are our X, linear regression, and that beta then is the linear combination that represents this new face, which we can then search in Solr or update if it doesn't exist yet. So, to kind of go through my little animation from earlier again. Drone comes up, face comes up, we detect the face, decompose the face into grayscale. I really got carried away with these animations. We have a linear combination now of our eigenfaces. We search Solr for that, a vector of length 130, which is much more efficient. And Solr then returns back, and Solr has a lot of built-in functionality for searching, like the closest, distance metrics. We're just looking at basic distance metrics. I think it's Euclidean in this one. And that's how we can do facial recognition. Now, you might have noticed, even though this is a Flink conference, I've now gone 10 minutes in, and I haven't said the word Flink yet. This is a simple, stupid version that you can just do with, a little Kafka, or you don't even think that. You just Scala and Solr. But you run into some problems right away. The first problem is, as you have a video coming in, you're getting inconsistent frames of the face. It bounces around as lighting changes. It picks out the face, but it doesn't always center. You have a tendency for it to want to add more faces because it's always bouncing around. It keeps thinking, oh, this is too different. This must be a new person. And then it will want to enter bad faces. You also get sometimes, because we're just looking at patterns, it happens that the light and a pattern on your t-shirt or in the background looks like a face, and for just maybe one frame or two frames, you're detecting something that's not a face. And those could get inserted into Solr as a face. And these are the big problems we have right off the gate. Now, it turns out that Flink has a lot of, the windowing in Flink really solves this. But to illustrate what I meant with faces, every time, in every video frame, it's picking up a different section of the face. So you've got this inconsistent. And when you break that down into Eigenfaces, the computer, which is stupid, thinks that these are all different people, even though it's the same thing. Now, because we kind of know something about the domain we're working in, and we know that humans don't randomly appear and then disappear, but if you are in one part of a frame of video or one section area of a frame of video and you have the same person, that's probably the same person. Even if they look a lot different for a frame or two, it's probably the same. And so we can use that contextual knowledge, especially with the windowing. And to do that, the method that I use is Canopy clustering. And if you're not familiar with Canopy clustering, it is an older clustering technique that is pretty cheap and dirty, but it's very fast. In 1 to 2 passes, we'll cluster your entire thing, and it doesn't require a lot of data. And the gist of how it works is it's going through a data set, which in this point is a window of maybe a 10-second bounded window of face rectangles. The first point that it finds is the center. And then everything after that, as long as it's close enough to that, within some tunable parameter, as long as it's close enough to the original point, then we say it's not a new cluster. And if something's really far away, it is. I've got some, surprise, animations that might make a little more sense out of this. So in this window, the first face was just determined to be a new cluster. All of these come in. Now this one wasn't within the predetermined space, so it became a new cluster, and that's how Canopy clustering works. Short version, pretty easy. It works though. And then what we do, we call them ghost faces. These little, my animation skip, but that face that was down here, anytime in the window we haven't seen, if that cluster doesn't have at least 3 faces in it, we say, you know what, that was probably just a kind of a ghost image. Let's not count that as a face. Let's not process that one. Seems simple enough, and it is, because once you already have windowing sitting there for you, being taken care of, that was all the hard work. It was some pretty simple little stuff on top of that, and there you have it. I took this earlier today. If you couldn't tell, I'm feeling a little under the weather and didn't want to try my hand at a live demo, though I am happy to play like at lunch. This is the view of the drone, and I also had a regression in my code. But you will see gray little boxes come up from time to time. So that's finding a person. That was a ghost, and I don't know why it did whatever, but it's not a perfect AI system, suffice to say. Yeah, as I'm watching this wasn't really a great example at all. My code really went to hell on me when I wasn't paying attention. So that's that, but that's the gist of what it looks like from the first person view of the camera. Remaining faces. So the old way, the cheap non-Flink version is going to think each one of these are different humans and then add 4 new people into our Solr database. Because we've windowed and we said, okay, all these faces were in the same cluster, they're probably just different frames of the same person. So we'll just add all of these faces to Solr, but we're going to at least label them all as human 1 or whatever name we've given this person. And so that's another, free bonus of just having a little windowing. A lot of things get a lot easier for us. You could really blow this out too with some complex event processing, and there's so many things, like I said, just off the shelf in Flink that are very turnkey that make this all a real easy and enjoyable experience. Windowing lets us use intelligence, but using context clues. Because we're all actual Flink users here, or maybe have at least heard of it, this might be more informative than my fun PowerPoint demos. This is the actual plan of the job. We're catching vectors. We're taking those in from a Kafka source. We've got a windowing function that is applying our Canopy cluster. This is happening, I believe, in 5-second windows sliding. we apply the clusters for every element that comes in, so we can do that as quickly as possible. Then that whole sequence that does the Solr, is it a new face, is it not a new face, making all those decisions, and then it loads the actual original images to make a nice pretty output for us. The thing really gets very not real time once you add this part in, because it's a very, writing buffered images to Kafka is a very inefficient way. It causes a lot of lag and back pressure. But everything up to there, as far as the facial detection, works in pretty good real time. If you're looking for something to actually do real-time facial. And this is not a particularly optimized anything, so there's definitely a good start here. Tying this back to buzzwords, artificial intelligence. Well, let's look at the definition of just regular intelligence. The ability to learn or understand about our environment and to apply knowledge to manipulate the environment. And applying knowledge is that key thing that differentiates machine learning applications from artificial intelligence applications, if we're to say there's any difference at all. And the words haven't all been thrown away. So any kind of IoT diagram is going to look something like this. You've got edge devices, sensors, cameras, as the case may be. Something has to collect these things, take and process the data. There's thoughts or understanding that happens, and then you want to apply actions back to something. You want to do something in the world, especially in the case of these drones. Turn the lights on different colors, maybe they follow someone around once they know. And that's, yeah. Now, as you're probably looking at this, oh yeah, bonus would be, so maybe offline learning can happen, memories. Now, you probably are guessing that this is all just a setup for a bunch of Apache projects that we can create a really, really nice first-class artificial intelligence engine out of off-the-shelf open source Apache. That would be the Lambda system, but it doesn't, and the system I've laid out is Lambda, but could be easily turned into a Kappa. But if we're going to consider, the higher brain functions like Mahout and the memories are Solr and Spark doing the learning, then a way we can think of Flink in this context of an artificial intelligence engine is Flink provides like the stream of consciousness and the short-term memory and the context of like, where am I? Oh, I've been looking at you for the last couple of minutes, even though you turned your head and now you look kind of different. I know that you're probably still the same person. You've just changed the face you're looking. And none of this maybe even seems like a huge step, or I'm like really jumping off an end, but it's because I think it just sort of worked out that it really solves a lot of the problems you want to deal with and you're going to come up with right away when you start getting into artificial intelligence kind of stuff. Is just a natural, that's what it does, is a streaming engine. So we don't think of Flink for artificial intelligence a lot, but I guess my thesis is that's not because it's not great for it. It's just because, for whatever reason, nobody's really been put it in that context. If you're a big sci-fi fan, all of this would technically not be Cylons. It would be more like the Borg with a hive mind, because the real beauty of this system, or the really cool thing, is one drone recognizes a new human, and then, all right, it flies off and does the other thing, and then his little buddy drone comes by 2 seconds later, but because they're tied into the same Solr and they can give each other context clues because they're all probably sitting in the same stream job, it really picks up fast that, oh, I've adapted, I already know who that is, I don't have to learn. I can pick things up really fast. So given an army of 5 or 6 or however many of these little guys you want, they can all work together in concert, more kind of like a single intelligence, if you will. So that being said, I think in the next few years we're going to see this kind of artificial intelligence on cheap little Amazon robots. This is science fair grade stuff. This is what your kids will do for like 5th grade, to learn artificial intelligence. There's nothing particularly complicated here. It's just cheap little toys. The whole rig out's not that much Flink code. It's a few window functions, If you're into machine learning on streams, there's a couple interesting like online clustering, quasi-online clustering algorithms going on. But more importantly, I think maybe a week and a half ago now, Vlad Putin said something about it being undesirable for one entity to monopolize AI. And I am not a fan, I'm not Vlad Putin's fanboy or anything, but I think that's right, that we don't probably want that, not just a government monopolizing it, but also a company, the Googles, the Amazons, the IBMs, the Facebooks. And so it's the sort of thing that makes sense. That would be good to be in the open source. And so when we talk about building these open source engines for artificial intelligence, that's where that belongs, where there's no real ownership and no one can ever get too much of a leg up on everyone else because there's some best in class artificial intelligence sitting right around the corner in open source. So my call to action would be keep donating. If this is the sort of thing that you're interested in, facial version, even the Flink stuff, building end-to-end pipelines and applying, just putting out examples or doing something in your day job, make and continue to make the Apache and the open source artificial intelligence the best in class, because that is really how we prevent anyone from running away with it and getting too powerful or getting too strong. And this is a video of a thing that I saw on Saturday. There's people just street vendors make like little robots that dance. This was a pre-programmed just sequence, but it wouldn't be hard to apply this artificial intelligence to this little guy. And that looks disturbingly similar now to science fiction robots that have intelligence. There's no intelligence on this one, but it could be grafted on with some of the things I've laid out earlier in this talk. So the future's coming. It's coming faster than we think. And that's the gist of what I wanted to talk about today. So I'm a little short, but I'll take questions and now or after. Ta-da! No questions? Okay. Go ahead. Okay. Thank you. I think the question was, when would you use Eigenfaces versus neural nets? I think you wouldn't. Eigenfaces you use for when you're going to be constantly running into new people and you need something that's going to scale really fast. You can be able to recognize people really fast. Neural nets will do a better job. They will be more accurate. If all you have is an image of someone and you have lots of time to look at that image, your neural net's probably going to be your best play. When you're doing real-time video at scale across maybe 50 cameras or 150 or 1,000 cameras, you could theoretically do it, but you're going to need a lot of hardware. And that's when I would say, that's when you start looking at things like Eigenfaces, things that they're not as computationally complex, but scale better in both hardware and time. Sure. The training time for Eigenfaces versus neural nets. Neural nets, again, long training time. The more convoluted and deep you want to make your learning, the longer training time is going to be. For a comparison, the training for the Eigenfaces, you're taking that big matrix and you're doing that matrix decomposition. I was running on a 32 gig of RAM, I think 8-core machine. It took me about 45 minutes to process. I used the 10,000 faces data set. So 10,000 images of 62 or 250 by 250 faces. So you're looking at 45 minutes versus several weeks. No, it was on my local machine. But that being said, Mahout will do distributed matrix decomposition. So both of them will scale out in hardware. But no matter how you ever slice it, an Eigenfaces is going to be exponentially faster. And what you would normally do in a real life situation while we're learning in real time, you could say every day or every month, you can take those faces you have and you can just recalculate, and you can recalculate your best Eigenfaces because it doesn't take you that long to do at whatever epoch makes sense for you. Yeah, it is. They're called the Petrones. On it. Yep. If you go, I didn't put it. I'll put it when the video posts up. I'll put in the comments the YouTube or the GitHub. But the GitHub has a shopping list that lists the drone model because it's the Petrone drone, and they're $50 a pop. But then you also get the little camera add-on, which are $30 a pop. And that's how you can kind of do it all. But yeah. Yeah. Yeah, it's for those, actually, I'll just say it in case it takes me forever because I forget. You go to github.com, Rockin Trevo, RAWKINTREVO. Yep, same as my Twitter, 100%, yep. /Cylons, CYLONS. And I'm probably not even hooked up to the internet, so I'm sure it's gonna. All right, well, oh no, it did work. So you get on here, and it has everything broken out into nice little modulars, and you can see the Flink code. There's a shopping list that will give you direct links to everything, and so on. No problem. The Har cascades. I didn't go, you know, you have some background information. The Har cascade filters are based on Har wavelets. I'm not going to pretend to be an expert in that slice. This was a good case of me going to an open source library. I'm like, oh, magic, got it. And I just used it. And then last night I was trying to read up. I'm like, ooh, I got to figure out how that works, or someone's going to call me out. And I just admitted it anyway. But that's, and you know, you do that sometimes. It's the beauty of open source, I guess. But that's, yeah, they are based on Har wavelets. You are correct, instead of neural nets. So, yep. You, yes, can if you want. Go ahead. Yes, there are. I took one of many possible ways to handle that Canopy function. You can definitely leverage Solr a lot more into that because really the score, if you will, is the distance. You're searching a vector in Solr, and you're sorting your results based on the distance of all the other vectors. And so in the cheap original version, the way I did it is I said I would set some fixed distance, and anytime the distance is over whatever threshold, then it's a new face. That's cheap and dirty, and it does it, but it's not great, but it's a way too, and it's really a hybrid of the two are probably what you're going to want. But yeah, if you look in the local engine on the GitHub, that's exactly what it does. It just does the ranking and thresholding. So yeah. Everybody feeling satiated? What's up? I picked Canopy on this because it will do it in one. It's cheap and at one pass. The T1 and T2 guesses. Yes, that was. I had a clever solution for that. Is why. If we go, so as I said on the Canopy clustering, there's a hyperparameter you need to set that is. Oh shoot. I don't know how to get this back. There we go. All right. There's a hyperparameter that you have to set of like how big of a circle do you draw around, then anything's in it. And the way I do that is I look at all of the rectangles in the window and I say whatever the biggest rectangle is, is my loose distance, i.e. the distance at anything further than that goes over. This is, again, a cheap and dirty solution on top of a cheap and dirty solution, but what is exciting about it is this is a machine learning model that is parameterizing itself in real time, for better or worse, which is in turn something that you can say, okay, is that a smart system? And it can maybe learn and update its own, hyperparameter setting. So is what it is. And it's an easy clustering model to kind of wrap your mind around, because it's just that easy. What's up? I don't actually, yes, that's the T2. The T1 in a true Canopy clustering model, you say, as you go through, if it's within the T1 distance, then the next face in this case would be 100% assigned to that cluster. I kind of made it dirty, and I said, anything within T2. The T2 and the T1 are the same, to answer your question. So that's what it is. And is it mathematically whatever? I don't know. I don't care. It kind of works. So you got to do it sometimes. Yeah. It does. Also in this code, when I'm actually testing it, I don't do it on the drones. I watch TV. I've got an online TV link. That adds some new complex challenges, because in that case, faces do randomly drop off and appear as they cut scenes or go to commercial or cut camera angles. But it still does a fairly good job of that, because where it would... Imagine if someone was standing right here. The faces that are going to be drawn are going to be about the same size. And hopefully there's at least one head spot between us. If we moved our heads really close together, the thing would get confused. Or if one person was standing up here, so the perspective of this head was a lot bigger than the one back here, you would also probably trick it like that. If that was the case, you'd have to update your Canopy, but yeah, but in general, as long as it's two people at about the same distance away, standing at a reasonable space apart, it has an okay time with it. Okay. Well, I'll be floating around all day, so if you want to know more,